Hello students, in this video I'm going to solve the PYQs, previous year's questions of AHS final examination under Assam Higher Secondary Education Council of the chapter Atom Physics class 12. Okay, so before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. If you get the option to hide, then please do hide the video. Okay, and if you want to follow me on Insta, this is my Insta ID OJHALAKHYAJIT123. that's my Insta ID. You can follow me on Insta. So now let's start. So here is the first question. Arrange the Bohr series, Lemon series and Paschen series of emission in spectrum of hydrogen in order of increasing order of wavelength. This was asked in AHS final examination 2025. So let me write the increasing order of this. So first you have to write Lemon series, then Bohr series, then Paschen series. Okay, so this is the order. So now let me take the next question. So this was also asked in 2025 AHS final examination. So state Bohr's second postulate and de Broglie relation of representing the matter wave using de Broglie's relation. Obtain the quantum condition proposed by Bohr for angular momentum of an electron moving in the nth orbit of radius Rn, speed Vn. Okay, so first let me write the Bohr's second postulate. Okay, it states that electrons can revolve only in those energy levels in which its angular momentum is an integral multiple of h by 2 pi. So where h is Planck's constant, right? So this is the second postulate. Okay, so that means suppose this is an orbit and here we have an electron. It is revolving around this nucleus. This is the nucleus, suppose positively charged nucleus, and this electron is revolving around it. If its angular momentum is L, then it must be integral multiple of h by 2 pi. That means value of m must be 1, 2, 3. It cannot be fraction, right? So hope you have understood this. So this is the second postulate. Okay, so now number 2 of this question, there is another part, that is this de Broglie relation representing the matter wave. Okay, de Broglie relation representing the matter wave is given by lambda is equal to h by p. P is the momentum. Okay, P is the momentum. So P is the momentum of the particle, right? Suppose we know that suppose particles, let us consider, and this is an electron. If it is moving, then an wave will be associated with this moving particle. That means it will have both character in motion. It will show wave nature as well as the particle nature. So it must have a momentum, okay, and a wavelength, as it shows dual natures, okay, the particle and wave, and wavelength of this that must be equal to h by its momentum. Okay, this is the momentum here. Okay, so here this is wavelength, and this is wavelength associated with a particle moving with momentum p. Okay, so hope you have understood this. So now here is one more part in this question. Okay, using this relation, obtain the quantum condition proposed by Bohr. What was the quantum condition proposed by Bohr? Is that this wave angular momentum, this L, is n times of h by 2 pi, where n is integer. Okay, we need to obtain this relation using this relation. So let me take this as equation number 1. Now you see here it is mentioned that speed of the electron is Vn, which is in the orbit of radius Rn. Okay, so now you see, now let me copy this equation number 1 and let me take a new slide. So here is the new slide. This is this one, equation number 1. Now you know, according to the Bohr hypothesis, according to the Bohr hypothesis, so an electron, you see, an electron can revolve in this orbit, okay, if the wavelength associated with this electron, okay, can divide the circumference of this orbit completely. That means if you divide the circumference with this wavelength, by this wavelength, then it should give remainder 0, right? Hope you have understood this. If this wavelength is lambda and the radius of this is Rn, this orbit is Rn, so its circumference is 2 pi Rn. That must be equal to integral multiple of lambda, which is the wavelength associated with the electron, where n is equal to 1, 2, 3, dot 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 dot, so on, right? Okay, so now you see, if m is equal to mass of the electron, moving with speed Vn, then what we can do, we can write momentum of the electron P is equal to m into Vn. This is momentum, right? This is momentum of the electron. Let me take this as equation number 2. Now if we use this value of lambda here, then what we will get from equation number 1, and from equation number 2, what we can write? We can write that 2 pi Rn is equal to n into, instead of lambda we can write h by p, right? H by p. And now let me do here, okay, 2 pi Rn, n into h, p means this momentum, m into Vn. Now if you simplify this, m Vn into Rn is equal to n h by 2 pi. Now this is nothing but angular momentum L, right? N h by 2 pi, where n is equal to 1, 2, 3, dot 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 dot. Okay, so this is the Bohr's quantum condition. Bohr's quantization condition. Bohr's quantization condition of angular momentum, right? So hope you have understood this. Now let me take the next question. Okay, so this question was asked in 2024, right? So here it should be here first one is small, so here it should be 180 degree for small impact parameter, and for large impact parameter the scattering angle should be 0 degree, right? So now let me take the next question. So here you see, write the following expression in words. So this is nothing but Bohr's quantization condition of angular momentum. So how to write this in word? Okay, this is Bohr's quantization condition of angular momentum which states that an electron can revolve in an orbit if its angular momentum is integral multiple of h by twice pi, where h is Planck's constant. Right, that's what we need to write. Now you see what is the second expression says. Now you see, if an electron in higher energy level, let me take this is EI, here EI is greater than EF, so it jumps from higher energy level to lower energy level EF, then it will radiate energy which is equal to h nu, right? Okay, so that is what it does say. So how to write this in word? Let me write here. So let me write here. Okay, so now you see, this is nothing but Bohr's third postulate. Okay, third postulates of Bohr model. Bohr's third postulates. Which states that an electron can jump, let me erase this, okay, can jump from higher energy level EI to lower energy level EF, radiating energy in the form of photon, h nu of frequency nu, right? Hope you have understood this. That's what we can write. So this was asked in 2024. Okay, 2024 HS final examination. Now let me take the next question. Okay, So now you see here in this question, so what we have, this question was asked in AHS final 2023. Okay, 2023. Now you see the radius of innermost electron orbit of an hydrogen atom is given. That means you can say this is R1, that is 5.3 into 10 to the power minus 11 meter, that is given. Calculate the radius of N2 second and third orbit. Okay, N2 and N3. So here Rn is given. So here Rn is equal to n square divided by m into h by 2 pi whole square 4 pi epsilon naught by e square. Okay, so now you see, first let me find R1 from this. That's going to be, instead of n square, that's going to be 1 square, which is nothing but 1, right, into m by m square. Okay, h by 2 pi square whole square 4 pi epsilon naught e square. Okay, now you see, if you find R2 for n is equal to 2, radius R2, that's going to be equal to, so here instead of n square, sorry, here we should have 1 by m, we have no square here on m, so this is simply m, so n square by m. So on putting n is equal to 1, we have got the innermost radius, right, so 1 by m. So if we put r is equal to 2, n is equal to 2, then we should get n square by m into h square by 2 pi whole square 4 pi epsilon naught by e square. So this is nothing but, you see, this is 2 square times of r1, this is 2 square times of r1, right? Hope you have understood this. So that's why what we can write that this is equal to 2 square times of r1. 2 square means 4 times of r1 is r1, what we have got r1, this is 5.3 into 10 to the power 11 meter. So if we multiply this, then what we're gonna have, so if we multiply it, then it's gonna be equal to 21.2 into 10 to the power minus 11 meter. If you make it 10 to the power minus 10, that's gonna be 2.12 10 to the power minus 10 meter in standard form, right? So hope you have understood this. So similarly we can write for n3, similarly in case of n3, r3 will be equal to, so r2 is equal to 2 square times of r1, so r3 going to be equal to 3 square times of r1, so that's going to be 9 into 5.3 into 10 to the power 11 meter. So if we multiply this, then we should get 47.7 into 10 to the power minus 11. If you write this into standard form, then that's going to be 4.77 into 10 to the power minus 10 meter. So that's what we have got. Okay, so now let me take the next question of this year. So here this question was also asked in 2023 AHS 2023. Okay, so term this term here, you can see a naught is equal to h square epsilon naught by pi me square. Okay, so what does it mean? This is nothing but Bohr's radius. So this is option number 2, right? So hope you have understood this. Okay, now this question was asked in 2022 AHS 2022. Sorry for this picture quality. Okay, according to Bohr's second postulate, if you can't read, then please listen to me carefully. Okay, write the question. According to Bohr's second postulate, quantization of angular momentum of electron in the first possible orbit. Now you see Bohr's quantization condition was, let me clean this first, that was angular momentum L is equal to n times, that means integral multiple of h by 2 pi, and for the first possible orbit, that means for n is equal to 1, so that's gonna be, let me write here, for n is equal to 1, for n is equal to 1, this L gonna be equal to h by 2 pi, right? So h by 2 pi, so option 2 is the correct option, right? H by twice pi. So now let me take the next question. This was also asked in 2023. Okay, write the mathematical expression for postulate of the postulate that an electron has to strictly follow in order to revolve around the nucleus. Name the scientist who proposed this. This was again Bohr's second postulate, right? This was again Bohr's second postulate, and the mathematical expression was equal to L is equal to n into h by 2 pi. Okay, so this was the mathematical, this is the mathematical expression of the postulate that an electron has to strictly follow in order to revolve round the nucleus is this. Okay, where L is angular momentum of the electron, angular momentum of the electron. Okay, so n is equal to 1, 2, 3 dot 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 so on. H is Planck's constant. Right, and it was proposed by Niels Bohr. Name of the scientist who proposed this. Okay, hope you have understood this. Now let me take the next question. So this question was asked in AHS final 2022. Okay, 2022, sorry, not 2022, 2020. We know that de Broglie wavelength lambda is equal to h by momentum, that is p, and for heavier particle the momentum is higher, so this wavelength will be very small. Okay, extremely small wavelength. And if you consider that the mass of the heavier particle is m, then we can write if it is moving with velocity v, then we can write that lambda is equal to h by m into v. And for a heavier particle it is very small. It will be better. In 1885, a Swedish school teacher observed a series of spectral lines in visible region of hydrogen spectrum, named the spectral series. Okay, and if the Rydberg constant is this, so here this constant is wrong. Here it's supposed to be +7, here it is given -7. Okay, it's supposed to be +7. Okay, and value of this 1 by 2 square, 1 by 3 square minus 1 by 2 square, 1 by 2 square minus 1 by 3 square is 0.138. Calculate the wavelength lambda of this H alpha line. So now you see this spectral lines are in the visible region of hydrogen spectrum was observed by Jacob Balmer in 1885. He was a school teacher of Swedish school teacher, so he observed, and in his name this series of spectral lines are named. Okay, so that's why here the answer is, that is Balmer series. Okay, so Balmer series, let me write it properly. Okay, so write the question, write the answer according to the question. Okay, so just I have given the answer directly, Balmer series. And here you see, here to calculate the wavelength, here we need to use this formula, that is 1 by lambda is equal to r into 1 by n square minus n1 square minus 1 by n2 square. So here in this case, this value of r is given here 1.097 into 10 to the power minus 7. Actually it's supposed to be plus 7. Okay, minus 1. So let me put here 1.097 into 10 to the power 7, and here instead of this we're gonna put this 1 by 2 square minus 1 by 3 square. Its value is also given. So 1.097 into 10 to the power 7 into value of this part, that is also already given, 0.138, 0.138, and if you multiply these two, you're gonna have 1.514 into 10 to the power 6, 10 to the power 6, sorry, let me write it properly, 10 to the power 6 meter inverse. So this is nothing but what we have got, 1 by lambda. Now we need to find a wavelength, that means lambda. So in order to find a wavelength lambda, we have to take the reciprocal of the 1 by lambda, that is 1 by 1.5 into 10 to the power 1.54, sorry, 1.514 into 10 to the power 6. So if you evaluate this, then you're gonna have 6.605 into 10 to the power minus 7 meter. That's what you will get, right? So this is the answer. So hope you have understood this. Let me take the next question. So here is the next question. A difference of 2.3 electron volts separates two energy levels in an atom. What is the frequency of radiation emitted when atoms make a transition from upper level to lower level? So we have two energy levels, and these two are differ by the difference between the two energy levels is 2.3 electron volt, right? If this is EI, this is EF, then EI minus EF is 2.3. The difference is given 2.3 electron volt. So we're gonna apply the third postulate, that is H nu is equal to EI minus EF. So here it is given 2.3 electron volt. So we need to calculate the frequency here. Okay, so now you see, convert this one into joule. Okay, that is 2.3 into 1.6 into 10 to the power minus 19. Okay, now it becomes joule. And what is the Planck's constant? So let me put the Planck's constant, 6.63 into 10 instead of 8. So this is Planck's constant, 6.63 into 10 to the power minus 34. Okay, joule second. So that is Planck's constant, right? Okay, nu, that is the frequency, 2.3 into 1.6 into 10 to the power minus 19 joule. So here this frequency gonna be equal to 2.3 into 10 to the power, sorry, into 1.6 into 10 to the power minus 19 divided by 6.63 into 10 to the power minus 34. So here we're gonna have second inverse, or you can simply write hertz. Okay, so that's gonna be the frequency. Now calculate this. Let me use calculator. If you multiply this to 2.3 into 1.6, so that's gonna be equal to 3.68 divided by 6.63 into 10 to the power minus 19 plus 34. So now what we will get, 3.68 divided by 6.63, that's gonna be equal to your 0.5, approximately you can write 0.56 into 10 to the power and here it's gonna be 15, right? Plus 15. So now let me write the result in standard form. Let me write the decimal here. So then it's gonna be 5.6 into 10 to the power 14 hertz. So this is the frequency approximately. Okay, so now let me take the next question. So this is another question which was asked in 2022. Calculate the energy in joule that is equivalent to 1 mega electron volt. So now you see, first let me convert 1 mega electron volt into electron volt. That's going to be equal to 10 to the power 6 electron volt, right? 10 to the power 6 electron volt. And now convert it into joule. We know that 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule, right? 10 to the power minus 19 joule, right? Okay, or you can use 1.602 as well. Okay, 1.602 into 10 to the power minus 19, almost equal to 1.6 into 10 to the power minus 19, right? So now let me convert it into joule. So 1.602 into 10 to the power minus 19 into 10 to the power 6 joule. So 6.02 into 10 to the power minus. So what gonna be the answer here now? 13, minus 13 joule, right? Let me take the next question. This question was also asked in AHSEC 2022. Okay, so let me answer this. So here we need to find the wavelength of H alpha. So it can be obtained by using this formula if you put n is equal to 3 here. Okay, so here Rydberg constant is given 1.097 10 to the power minus, so it's supposed to be plus 7, okay, not minus 7. So it should be plus 7. Okay, so let's find the values. 1 by lambda, let me put the Rydberg constant 0.97 into 10 to the power 7, and 1 by 2 square minus 1 by n square. Here we're gonna put, instead of n square, we're gonna put 3 square. Okay, so now let me calculate these values. So 1.097 into 10 to the power 7. So 1 by 2 square means 1 by 4, that's going to be 0.25, right? Minus 1 by 3 square means 1 by 9. 1 by 9 is approximately equal to 0.11. You can write this. Okay, now 1.097 into 10 to the power 7, that's going to be equal to 0.14. Okay, so we need lambda, so it is 1 by lambda, we need lambda, so that's going to be 1 by 1.097 into 10 to the power 7 into 0.14. okay, so that's gonna be 6.5 approximately into 10 to the power minus 7. That's what we will get, meter. Okay, so that is the wavelength of H alpha spectral line. Okay, so this is the wavelength of H alpha spectral line. So now you see, we need to arrange these three spectral lines, H alpha, H beta, gamma, in decreasing order of their wavelength. So in decreasing order, so this is H alpha, H beta and H gamma. Okay, its wavelength is shorter than this one and its wavelength is shorter than this one, right? So that's the answer. So hope you have understood this. So thank you for watching. See you in the next video. Bye bye.